All right, Mary Baldwin students, Dr. Tausman coming to you live once again from Roanoke, Virginia. Hopefully you have your textbooks with you. I'm going to start talking about some statistics once more. The relevant chapter would be Chapter 10, Introduction to Independent Measures T-Tests. Looks like page 317. So I have on the first assignment a little case study. Read through that one. A new drug is out there. Give it to 3 people. Ask them to rate their pain an hour later on a 10-point scale. Higher number means more pain. 3 other people, they get the drug. Their scores are 1, 2, and 3. I do the same thing for 3 other people, but give them a sugar pill instead. They get scores of 5, 6, and 7. So the key question is, does the drug actually really work there? And so in this unit, we learn about doing t-tests. And a t-test is a little bit different than doing a z-test, because when we used to do the z-test, some of the recordings and the descriptions and the other information I shared with you, we know everything about the population. But in this particular example, look what information I'm actually given. I'm just given 3 people that get the drug, 3 people that don't. And so I just have 2 very small samples here. And so when you have 2 samples and you know nothing about the population, the relevant statistic to use with 2 groups when you have this situation is a t-test. And if you look on the picture on figure 10.2 on page 317, basically the idea is you have 2 samples here, sample A and sample B, and you're trying to figure out stuff about the population. And you basically have to use all the information from the sample to estimate or to figure out information about the population. And so a t-test you use when you know nothing about the population and you have 2 groups like this, and your dependent variable is something measured on a continuum. In this particular case, we've got the pain scores as it would be here. So if you look at formula number 1, that gives you the z-test formula. There you have to know the sigma of the population and mu of the population, the standard D and the mean of the population. In this situation, we don't know any of that. So we can't really use the z-test formula. Instead, we have to use the t-test formula, and it's in this chapter as well. That's where I got it from. Look at this formula, though, down in 2A. It kind of looks a little bit scary, doesn't it? Let's break apart kind of the numerator and denominator. If you look at this statistical situation in the numerator, we have x bar 1 minus x bar 2. Did you notice in the previous one with the z-test, you had an x bar, but then you had a population score. So in this one, you take the mean of the first group and the mean of the second group. Can you pretty much figure out what this number is going to be? Yeah, what's the mean of the first group, the people that get the drug? It's 2. What's the mean of the group that gets the sugar pill? It's 6. So the numerator for the t-test here would be pretty simple. The numerator is 4. And do you remember what you call that numerator? You call that numerator the treatment effect. And so the idea is you really want that treatment effect to be large, saying that the drug really does work. The denominator. Oh my God, look at that formula. S of P, 1 divided by the square root of, or 1 divided by N1 plus 1 over N2. That literally translates, if you go down a little bit into C, it literally translates into something called the standard error of the mean. And that's what we went over with the previous discussions. The standard error of the mean is how close is the sample mean to the population. Anything that has the word error in it, we want to be low. And so the idea is when you do this particular situation, the idea is you want the numerator to be large, the treatment differences to be large, and you want the denominator, the error, to be low. And that's the idea behind that. That'll do the first recording. Thanks. Bye-bye.